was expecting to see you in the chat messages. So is that okay now?
Yeah, I didn't know if you were gonna like looking or not. Like you didn't. I don't know. You responded to one as well. Yeah.
Yeah, sometimes uh, well, I got you. Sometimes I forget to look at the chat messages. Right, I've got them here right beside me on the slightly towards the left, and I'll check every once in a while. All right, program number 4. Every CPU has a clock. Every microprocessor has a clock, but it's a really dumb clock. It can't give us hours, minutes, seconds, or anything. All it can do is it makes ticks. Ticks at a rhythm that's constant intervals. At constant. And the correct word in clocks is not rate of the clock runs at. The correct word is frequency. Frequency. Okay, so a long time ago, 20 years ago, when they made microprocessors, there was a tiny piece of crystal rock, less than a half a millimeter on each side, a tiny piece of crystal rock, and with a microscopic cable, they would apply some microvolts to it. Tiny amount of electricity. And then that little crystal would kind of shake back and forth. So you could put a piece of metal on that side and a piece of metal very close to it. And as that shakes, then it closes the gap and electricity would flow. When it shakes the other downward direction, then the gap opens, electricity stops. But the neat thing in nature is that crystal would vibrate at a constant rate without fluctuation fast and slow. Well, in the modern time, they use no more crystals. I've read they use rare earth metals like titanium or some other rhodium fits that requirement that it vibrate at a very fixed constant rate, constant frequency. Anyways, the principle is still the same, and clocks, that little crystal or the rare earth is the center of the clock, and it each time it vibrates, that's called a tick. Equals one vibration. Okay, and by putting that little electrical gap that opens and closes, we can count ticks. So all of our computers have a microprocessor, the central microprocessor, and it's counting ticks as long as the machine is powered on. So, yes. Okay, so there's a counter inside that we can't see, but we can extract the number off that counter with a assembly instruction. So it's counting, it starts counting at 0 when you power on. Count starts 0 when you boot up. Okay. And to get the count number out of the microprocessor, we use two assembly instructions. Let's see, CPUID, followed immediately by RDTSC. Hey, is that under the? I hope that's under the the camera. Let's see. Make that happen. Okay, and I'll try and the first one is hard to explain, but it's not the important one. The important one is the second one. When your computer's running, there's a lot of processes running in the background that you never even started. They were started by the root process. So these processes are running, there's sometimes like 100 of them. These processes are running all the time, and CPU ID makes them all pause for one tick, for the duration time of one tick. All those processes must stop, and then they resume immediately thereafter. So processes, it's more than, it's not stop, it's pause. Okay. And what it does is it lets the next one read the clock at an instant when everybody's paused. And why do you want to do that? The reason is the clock is often used for benchmarking the speed of execution. Benchmarking refers to testing some software to see how fast it executes. And to make a good test, you want the software to stop. You read the clock, and then you let it run and do its job, and then you stop it again and read the clock, and then you subtract the difference between those two reads, and you have how long it executed measured in ticks. That's the problem. Okay, let me give you an illustration. What is the here's a something we know about. Add SD, and it doesn't matter which one, XMM3, XMM4. Suppose you want to know how long does it take for this instruction to execute. What will, oh, you can't loop it. This is really dumb. You write a program that says add 100 times. So you put that statement and then you do it again. XMM4. And copy and paste it until your whole program is simply to do that 100 times. Got it? Okay, so you read the clock at the beginning. You get the number off the CPU clock. Execute the instruction in sequence 100 times. (100 times). Then you read the clock again. Then you know how long it took to execute it 100 times. Then you divide the difference of these two clocks by 100, and you have in principle how long it takes this instruction to execute one time. Okay, there's somebody on the web and posted in Europe who's done this test on all the instructions in x86 assembly, all 709 of them. It's a tedious process, and I don't know why he did it, but he has them all listed at his website. The execution time for every single instruction. Okay. Well, let's come back to our project. This clock is often used for benchmarking and finding how long something requires to execute. And you get an answer. Let's make it over here. It's just under the clock, under the. Okay. So let's say we read the clock at one time. And the official function that does that is RDTSC. So we get a number, ticks, number one, and that's some number, 48,732,622. And then we execute some stuff. And then we read the clock again. And we get another number of ticks, number two. And then we subtract them and we have elapsed time. Equals T ticks number two minus ticks number one. Okay, there's your elapsed time measured in ticks. Okay, but most humans can't relate to giving the time in ticks. We'd like to know it in seconds. So assignment programming project number 4 wants the time in seconds. So to get the time in seconds, we need to know the frequency of the clock. We need a clock. Okay. A clock. Okay, so how many times does it tick per second? That, and these are public numbers. You can read the specification about your own computer. When you buy your laptop, it'll be in a box, and then there's some system performance numbers on the outside, and it will tell you your clock is running at 2.8 gigahertz or 2.25 gigahertz and different stuff. An overclocked computer would be 5.0 gigahertz. Okay. And all those numbers mean, when we say it that way, we mean 5 billion ticks per second. So 5 gigahertz is easier to deal with than 5 followed by 9 zeros. And that's equal to 5.0 times 10 to the 9. Okay. So remember this 10 to the 9 issue, we come back and deal with it. Ticks per second. That's its frequency. And oh, I forgot to tell other classes. We'll do it now. The frequency in modern computers can vary, not because of the crystal is broken or anything, but that's intentional. Okay, let me back up. Remember I said you apply a small amount of microvolts here, microvolts, okay, and then you keep the electricity going and it vibrates at a fixed rate. But if you reduce the microvolts to less, it vibrates at a lesser fixed rate. Okay. So modern computers, the clock declines to a minimum when it's not active, and it goes up to its maximum when it's under load. Okay. So there is actually a min speed, a min frequency, and there's a max frequency. Okay. So it's set at the factory that you can't apply too much electricity and exceed the max frequency. And there it's also set that you don't drop below any too low. You can't lower the electricity till it actually stops. So I checked my own machine. It was 800 megahertz at the min, and 32 megahertz at the max side. So when it's actually doing work, it will tend to go raise its frequency to its max. And when you walk away and it's just idle, it will lower its frequency to 800, in my case, to its minimum 800 megahertz. All right, so well, we need to get the frequency off your computer, and some students created a function 3 semesters ago, and I also tried to make one called get frequency. And there's one posted at the class website, a copy of this, and there's others posted, I've been told. There's links to it in Discord. You need one of those functions, and its prototype looks like, as far as I know, they all work. Double frequency, double get frequency. No parameters needed. It acts like that. And so with no parameters, there's basically no setup to get this frequency. And it'll give you a float number. What do float numbers look like? They look like these. Okay. So you're going to get a number that looks like 2.8, for instance. And that's measured in gigahertz. Yeah, go ahead. Right paper here, yeah. Okay, remember the problem is to do this division. Elapsed time equals ticks later minus ticks earlier. And we want to divide by the clock frequency. Now, here's the issue. The number that the function gives you is in gigahertz. We want it just in hertz. So you have to divide by get frequency. Is this visible in the camera? Okay. Get frequency times 10 to the 9. Okay. So the frequency number, like 2.8 times 10 to the 9, which is 2,800,000,000 ticks per second. Okay, so if you divide by that number, your answer will be a time interval in seconds. Right? That gives you an answer in seconds. Yeah, let me see if there's any questions. Any questions so far? It all makes good sense, I hope, to you. Okay. Let me think. Where do we? All right, we know how to get the frequency. We need to know how to get the ticks off the clock. No, I didn't say that quite right. The frequency comes from the clocks making ticks. How many you can do in one, how many it can do in one ordinary second. The other one is, remember I talked about get the number of ticks. Okay, so it's CPU ID, and that's a preliminary instruction, followed by RD TSC, and that takes a copy of the counter from inside the clock and puts it in 2 registers, but they're split. There's why. It puts this part is how can I write it? This is RDX, and right next to it is RAX. Okay, so from the clock, that number is split here. And the higher order bits are over here. 32 bits here, 32 bits here, and zeros in here. They did this historically. It's too late to change it now. You're probably saying, why don't they just put the whole clock number in a single register and be done with it? Well, it's sort of to make things backward compatible with early Pentium Intel CPUs. It's too late to fix this now, but this is the way it works. RDTSC reads this hidden clock and puts the count of ticks split in two registers like this and this. What we want is the count of ticks to be in a single register so we can use it like in that place right there, or later on in that place. How do you think to do? You got to do this. We have to combine them into a single register. Let's do it. The strategy is to take one of them. Let's take this RDX one and slide all those bits on the lowest 32 to become the highest 32. Okay. So we're going to convert this into 0011010 imaginary divider place and 00000. So these 32 are sliding over to here to become this part. These are new entries here. New zeros. And this, whatever it was, got lost in outer space. It's just discarded. So how do you make the slide over? Well, to do that, there's an instruction not called slide, it's called shift. Shift to the left, SHL. And then you take any general purpose register like, I'll just pick on R12. And you say shift it to the left 4 places. Then it's going to take all the bits and slide them to the left. And the 4 that are already on the left get tossed away. And the new space that opens up on the right is filled with zeros. You follow that? So there's a register. 11010011. And you say shift left 4. Then what do we have? This over here, those 4 just fall out into outer space, and we're left with 001110000. 4 new zeros entered on the right side. 4 bits that were on the left side have disappeared, and everybody moved over. Okay, so let's go back to the clock problem. The clock problem is we want to combine those two numbers, so we're going to start from right there. Just under, yeah, that's probably, there it is. So the next step, the first step is these two. Step 2 is to shift to the left RDX. And now, can you see the, I'll write it again. RDX now looks like, oh, I forgot. We're going to shift to 32 places. 32 bits gets moved over. Now RDX is, all those zeros are gone. All this is moved over. 0, 0, 1, 1, 0, 1, 0. And I can't screw it in. And there's 32 new zeros attached in here. That's what it should look like. And I'll right underneath it, let's put RAX. And I'm copying it from up here. It says this is all zeros. Here's the divider line. And then this one is still there. 1, 0, 1, 0, 1, 1, 1, 0. Looks like that. Well, look at it. It's really nice because if we add those two, it will start adding over here, but there's no carry bits. 0 and 1 is the same. 0 and 1, 0 and 1, 0 and 0, 0 and 1, 0 and 0, 0, 0, that is, and 1. Nothing overflows. There's no carry bits. It simply combines the two registers. Let's write it out. So here's the next step. Add RDX, comma RAX. And the end result is that this one now has our complete number. It will look like 0, 0, 1, 1, 0, 1, 0. Invisible line. 1, 0, 1, 0, 1, 1, 1, 0. This is RDX. That's the ticks from the clock. That's it. Okay, so now you know how to get the, we'll call that reading the clock. You know how to read the clock. It's in these steps. First here, second here, third here. And then you have the clock in one register, and you save that. You save that number. Maybe put number 4 is, put it in a safe place. Move R14 RDX. Why do I call it a safe place? It's because RDX is on the list of parameters when you call a function. It's the third one on the list. RDI is first, RSI is second, RDX is the third one. It may get reused before you're done with it. So here we have a copy, and now R14 has the number of ticks. Yeah, let's see. Anybody have a question? That should work. Okay, so then you have to have two. I'm looking back here. You have the late ticks minus the early number of ticks, and then you divide by the frequency function, and then divide by 10 to the 9. Oh, but think about it. This is obviously done in floating point. This is not integer arithmetic. In fact, get frequency gives you a floating answer. Remember, its return type is double. So you got to get all those numbers over into XMM registers. You know how to do that, don't you? We have number of ticks in R14. What do? You say step 5. CVT SI to SD. And that was in R14. Let's use XMM 14. And now we have that number of ticks inside of XMM14. And you do the same thing for the second number of ticks. You can subtract them using XMM14 minus XMM15. Get frequency gives you a number. So when you're going to call get frequency, the setup is almost non-existent. So I'll explain that one. IX0 call get frequency. And the frequency value is placed in XMM0 as the frequency. Okay. So why I put 0 there is there's no RAX counts how many XMM registers are used for passing in data. The best I've ever experienced is it has nothing to do with returning XMM0 or returning RAX, returning float or integer. That's not what it's counting. It's counting how many XMM registers are used to pass data into the function, and get frequency has no parameters, so it's a 0. It produces one answer and it puts it here. Okay, and you're all caught up. We'll get through this pretty well. Quickly. Let's see. And then you have to figure out how do you going to get 10. What is that number? 1 billion. You have to get that in an XMM register in order to do that division. What about 10 to 1 billion is 10 to the 9. You know what? I would just put it in RAX and use the convert function. You decide how you're going to do that. Move RAX, comma, 1 billion. That's 9 zeros. And then CVT, SI, to SD, SD, X, and oops, X, and 8, RAX. So you got 1 billion in XMMA. Okay, what do we have to do? Anything more? No, it just gives us the answer in seconds. Okay, I'm thinking hard. Am I missing something? I think I'm missing something. I can't remember. Okay, we'll go off to, let's put that, let's change subject here. We're still on program number 4. Program number 4 says find, its name is find harmonic sum. And with the harmonic part of it means somehow that has been interpreted to mean do something with reciprocals of other numbers. So if you took all the ordinary integers, 1, 2, 3, 4, etc., and you turn them upside down, you use their reciprocals and you sum them all together, you have a harmonic sum. Okay, that's a harmonic sum. And what we want to do is that there's an input of n from the keyboard, n integer, You input from the keyboard, and then you compute this sum, which is mathematically written as and we want that number. Okay. And some other day I'll tell you why we want that number. It actually solves a number of 4 or 5 really important application problems. There are applications that need that number solved for different values of n. And looking at it, it looks like all integers, but when you do this work, they're not integers. These are float numbers here. Okay. The counter on the loop is an integer. That's true, but the adding them together to get the sum is a float operation. So you take all these reciprocals and have to turn them into a float number, and then start adding them all together in a big loop. And we need to know that. So let's see. Let me, I'm going to switch, I'm going to share a screen. Let me see if I can find it. Did I hope I left it here. Let's try this. Something's, what's wrong here? I can't get my, don't go away. I got a technical glitch here. Can that really be the case? Okay, what's the matter with my machine here? Okay, try. It's in this other directory. Oh, no, that's not the answer. What's the problem here? I don't know. I had a, maybe I gotta just tell you you need to download assignment whatever, program number 4. I was gonna screen share it, but I can't find, it won't load my file. I'll try one more time. You just keep searching and searching. Well, that's not good. I don't know what happened. Okay, I think I can. Don't go away. I gotta fix this. I know what it is. Okay. It's on a flash drive. I need to switch flash drive. So don't go away. I'll fix this. Eject this one. Okay. Check in this next one. Okay. Let's see how it goes. It's still not going to do it. Okay, I don't know what it is, class. Oh, I'm gonna go on without that. Okay, so what I was trying to show you is that Remember on Monday, I was talking about when you're going to start a project, one of the first things you think about is how can I subdivide this into smaller, manageable pieces? And I often provide you the first attempt at that. So I was going to show you the diagram. And by the way, there's many ways to subdivide a problem into smaller pieces that are manageable. I just happen to use what's called the calling chart, the calling diagram. So a driver calls a manager function, calls harmonic. I think it's coming back. And then that one calls output one line. Yeah, I wanted to show you the diagram, the picture. One line, because it make more sense. It doesn't branch out in what I think, but I might be wrong because software engineering is half science, half art. Another person equally well experienced could come along and say that's not the way to break it up into pieces. I have a better plan, but so be it. So the driver calls manager. The manager says input your integer, input the n. That's the number of terms in the harmonic sum. It could be 50, it could be 5,000, it could be almost anything. It could be 2, in which case you get 1 plus a half added together. 1 over 1 plus 1 over 2 added together. It can't be negative. Okay, so it gets that number and passes this number down here. And this one is the one that starts a big loop. This loops from 1 to n. Loop from 1 to n. Okay. And that does the big work. It has to grind out all these integers, especially if you start testing it with numbers like 500 million, 500 billion, and so on. It's a lot of work inside of here. W for work. Okay. If it's there, if you get your input number significantly big, then this one runs a long time, 2 minutes, 3 minutes. What happens to the human person watching? The human person gets bored and wonders, is my machine still working? Did it silently crash on me? So in many applications, they show you a progress bar going across left to right, and you can watch and you know that it's still working. So here we don't, in the terminal window, we don't have progress bar, but we sort of don't have. But we're going to use displayed output at fixed intervals. Okay, so too bad I can't show you the picture. Okay, so let me see if I can describe it well enough. Okay. So this is the one way of doing a progress bar. It's not graphical, but it's character based. Okay, so the dialogue goes, please enter number of terms you want to compute. Number of terms. Okay, imagine the user inputs, I gotta come up with something nice. 750, 755. Okay, So what you do, what your program is supposed to do is divide by 10 and truncate the remainder. So you divide by 10, and that results in a 75 quotient. Okay, so then your machine starts it starts computing the harmonic sum for 755 terms. And so after term number 75, I'm going to make a table here. Term number and harm value. Then you get one line output. It says 75, and the harmonic value is 4.27630. Okay, then it goes to work, and it works, it does term 76, 77, 78, 79, and it reaches 150. Then you get an update here, 4.89720783. Then it goes to work, does some more calculations, more terms, and at 225, you get a new update. So your user is not getting bored to death. And then 75 more terms go by, and you're at term number 300. You get another update. Okay. So at intervals of 75, that's what we're working on. Every 75 terms, you get an update, and then your user, remember, programs are never made for yourself. They're always made for somebody else. Your user is not bored to death and keeps seeing stuff appear on the monitor, and that's a good sign. 375 will be the next one, 450 will be the next one. And eventually it gets to ... It gets to 750. And you're getting an answer that's pretty close over here. 7.3984076. And there's 10 of them. We always like 10. But you're off by a few, and so you have to do one more, which is number 11. 55 7.3986401. Then you're done. You've computed the harmonic sum, and it's this number over here. Okay, so you get the idea. This is the terminal way of showing progress of a computation that's in progress. I don't think you have problems with that. Okay. Well, we're getting close to the end of this. I'm trying to remember if there was any other item in this. Oh, so see this one's looping back here. This one's looping. And it counts them. And whenever you come to a multiple of 75, like my picture shows, 75, 150, 225, then it calls this one time. This function outputs these two numbers. And then it goes back, it finishes, it goes back at looping and looping. There's no more output from here, but it reaches a multiple of 75. Then it calls this one for one more line of output. Get the next line of output. I think this is in C++. Easy formatting. You get two numbers arrive, one integer and one float, and you output one line, and then this one called one line is then done. When this one is done and it's completed the last calculation, number 755, and here's the answer, then this one returns that answer back to here, And eventually this one sends it back to here, which outputs the harmonic number. Got all that? Well, that's the walkthrough. It took us an hour. Anybody have a question? The lecture part's coming to an end. And I think you'll do it. I think you'll make it. Remember, if you stare at a description of a whole project, it looks threatening. Where's my diagram? You want to partition it. Oh, that's right here on top. This is the partitioning that I suggest, so that you can work on different pieces one by one. Most people start up here and do them downward, but it's not really necessary. You could write this one in C++, and I'm pretty sure it's not assembly. C++. And then you say, but does it really work? Well, you make a 2-line main program that calls this, and you send it 2 numbers and see if it will output it in the right. I lost the page, so it looks right. I lost the page. I still lost the page. Well, okay. My idea, what I'm trying to convince you is those emails that came to me and says, "Hey, professor, your assignments are too hard. I don't know where to start. I don't know where to start." Now it's only like 3 or 4 of those kind of emails, but it might be reflecting other people's attitudes too. What if they're your boss at work, your team leader gives you something really huge, not even just this assignment, but something's terribly huge? Are you going to go back to the team leader and say, "I don't know where to start"? No, you should analyze it and see if you can separate it into parts. Each part was much more simple than the whole. You have a chance then. Large programs, you have to approach it that way. There's no other way. Now, how you'd split it up into simple parts is a matter of software engineering science. I don't know that answer. There are different ways to approach that to make pieces that are manageable. This is my suggestion, and if you have a different one, hey, use it. I'd be pleased to hear about it. But this seemed like a logical outcome from the description of the requirements description of the program. Manager could be a little bit of work, but it really isn't. It inputs one integer, and then it calls this guy to do the work. So driver, you already have experience. That's always simple, Kate. Manager in this instance looks pretty simple, and this one looks like a piece of cake too. It's just one line of output. This one, you got to loop it and transfer all that stuff from integers over to XMM registers. This could be, if there's any work to do, this would be where it is in here. Your counter is looping from 1 to 2 to 3 and so on up to n. But for each one of those numbers, you have to do a convert to SD, and then when it's in XMM form, you have to take its reciprocal and add it to one register, which is known as the sum register. But actually, that's not bad either, because when you're doing this one, you're just viewing its pieces alone. You put all these others out of your head. In a commercial software development area, these will be assigned to different people to do. And you don't even think about their issues. You just think about the one you're working on. And if you're assigned to do this one, it sounds like a lot to do, but it really isn't. You can set up a loop that counts from 1 to an input number. And at each iteration, you have to find the floating point reciprocal of the loop control variable and add it to another XMM register. And you repeat that loop. Oh, you do have to, I left out one. You do have to test the number to see if it's a multiple of that quotient. Remember the 75? How do we do that? You want to see if the remainder is 0. So you have if you're running this one for k equals 1, k less than n, k plus plus, then in the body here, you have to find out, let me declare R for remainder, R equals k percent 75. If R is 0, then call one line. If it's not and after that you go on and you have to compute the reciprocal of k and add it to the sum. But how do you translate that from C++ to assembly? Oh, have we ever done that? Let me just take 3 minutes and show you that. Okay, let's say I'll do it in black so it shows it better. Okay, I'm going to do this loop. So let's say let R12 be loop counter. Loop counter. Okay, and let's let n has to be somewhere. R15 is n, last number in our iteration. Okay, and then where's 75 stored? We have to take. Oh, okay. Let's do. N is an input from the keyboard, but we have to divide that by 10. So let's let. We need a place for it. This is it, and we have put 10. So move R14 is available, make it 10. And then will this get up into the billions? Let's do the short way. These are unsigned integers, so it's div R15, R14. And we just lost the n. I should have saved the backup copy of it. So now the quotient is in there, but we don't care about the quotient. Everybody, while we're talking about this, let me do it. There's something to be learned here. Okay, I want to divide n by 10. Here's a more sophisticated way. Move a copy into RAX. So that's 10. Excuse me. That's the n number. The n number, like 875. All right. Now, CQO is going to extend that over a big range. CQO. That's from, do I have that right? Yeah, you see the Q for quad and O for octal, and C is convert. Okay, so RAX is extended to become RDX with RAX. 850 was in here, but now 850 is in this pair. That's an octal word. Okay. Now our 10 is in R15, and we can say div R 14. That's where 10 is. And the outcome is that RAX has the quotient. Which we don't care about. We're going to discard that. But RDX has the remainder. And now we check RDX. If the remainder is 0, you're at a multiple of, let's see, that, you know what? I think I was supposed to put 75 in there. This would give me a multiples of 10. RDX is 0 when there's multiples of 10. I'm looking back at my work. I think this better be the 75 number. So this is the remainder. If RDX is 0, I have to. So here it goes. CMP RDX with 0. Jump not equal. If it's not equal to 0, you just go down here and compute the term. But if it is equal to 0, then we call the one line. So I don't leave myself enough room, but I have to move the counter to RDI, comma, what's our counter variable? Do we have a counter? Loop counter is 12. And move, I haven't specified it, but we have to move to all XMM0 where our sum is located, XMM12, and call one line. Okay. So if these are not equal, you go down here and you don't call one line. But if these two are equal, the remainder is 0. Therefore, you go over here and do a setup, and so you can call one line. One line needs two numbers. One integer, which is the loop counting number, that's up here at R12. And the other one is the accumulated harmonic sum number, and you put it in XMM0. Those are the two passing registers. That's the first one for integers and the first one for floats. And then you say call one line, and then you come back and compute the next term. And then there's an iteration here, which I haven't figured it in yet. But that's how you get the remainder. I don't think I ever lectured on that before. Let's just make it solid in your mind. In C++, if you have two integers, int k and int j, okay. and you're going to divide them. K divided by J gives you a quotient and a plus a remainder. Okay. So we need an integer R. So it would be R equals K percent J. Or we're not concerned with it, but if you wanted that one, it's K divided by J. Q for quotient is the K divided by J. Okay, both of these exist in assembly very, very nicely. I'm going to do it now in assembly just to illustrate division of integers with finding a quotient and a remainder in the same operation. One division does them both. Okay, let's suppose, let's have R12 is K, R13 is J, and R14 is the quotient, will be the quotient. R15 is saved for the remainder. How do I solve this? Here it is. You take the numerator, the 12. Here's the numerator. And you put it in RAX. Move RAX R12. Then you expand RAX from its 64 bits to 128 bits. CQO. That instruction only acts on RAX. If you want to expand a number in some other register, you got to move it into RAX first. So now numerator equals two registers working together. RAX. Then you say, if these are unsigned numbers, you use div. If they're signed, you use idiv. I'm going to assume they're unsigned. So div by R13. It's one parameter because the div assumes that the other parameter is, the numerator is in RAX. It's in this pair. The outcome is that the quotient is in RAX. So we want, there it is, move R14 RAX. See, the div put the quotient in RAX, but we're saving it in R14. The div also put the remainder in RDX, but we want to save it in 15. RDX. When it does the division, it computes both numbers at the same time. It puts the quotient in R, that's a D down here, in RAX, but you move it someplace safer. It puts the remainder in RDX and you move it someplace safer, like R15. That's how integer division works. It has these two aspects, quotient and remainder. Okay, class, I think we're over time for the lecture. The administrators told me this is supposed to be structured 1 hour a week, 1 hour for, actually 2 hours a week for lecturing, 2 hours a week for open discussion. We do 1 hour of lecture 2 times a week, and we sort of use up today's hour. Okay, programming is supposed to be fun. It's not something where you go do your GE homework every evening first because you so are opposed to programming. Programming is a fun activity. It should draw you to it naturally, but you need the understanding of how it works. If I threw this at you and said, go find the remainder, then there's a bunch of research to look up exactly how to do it. But when you know all the tools, it should be a fun activity. Um, it's as fun as those science students who do experiments in the lab and they say, yep, my experiment works, or whatever they're doing. So, okay, I'm gonna close the lecturing time. I'm just gonna hang out here until 4 o'clock. If you got things to do, I understand that. I hope you have a nice evening. Don't forget one more thing. The assembly, the SI instruction will be at 5:30, 5:15 today, p.m. Um, if you haven't been going there, you should make friends there and get acquainted with Johnson, the SI leader. Um, ask him programming questions that are focused on something you want to really know. The question you can't ask him is, how do I get started? I don't even know what to do here. You got to do the first module yourself, and then when you're stuck, ask me or ask Johnson, and we'll both come up with ideas for you or solutions for you. Have a nice afternoon, everybody. See you next week.